Hello, I'm Alister Johnson, a fifth-year PhD student at the University of Oregon, and I'm going to talk about the work on automatic code rewriting that I've been doing as part of an internship at Argonne National Lab. And as a quick disclaimer, this presentation was made in mid-October, so things may have changed since then, and this was also presented at the LLVM HPC workshop at SC21, so you may have already seen it there. All right, I'll start off with a quick motivating example for the work I've been doing. One of the major rewriting or refactoring tasks application developers do is updating the APIs their application uses. For example, switching from CUDA to HIP, although the work I've been doing is in no way limited to CUDA or HIP. Sometimes these updates are simple, like the one shown here, where you can simply do a search and replace for CUDA malloc with HIP malloc, but other changes are not so simple, like changing from CUDA's kernel call syntax to HIP's kernel call syntax. There's no easy way to do the update here, except maybe by using sed or awk, but building the regular expressions to do this is going to be tricky and error-prone unless you're some sort of regex ninja. And of course, for this particular example with CUDA and HIP, there's Hippify, but what if you want to do some custom transformations? Hippify doesn't allow for any kind of customization out of the box, and if you wanted to extend or specialize it, you'd have to wade through a few hundred lines of code dealing with the Clang AST, and no one wants to do that, least of all application developers who have never dealt with the Clang AST before. But our compiler can still parse both of these kernel calls, and wouldn't it be great if we could leverage the compiler's front end to do these more complex rewriting tasks? If we could tell the compiler that with just a simple function attribute and ordinary C++, hey, find all of the pieces of code that look like this generic CUDA kernel call, and again, with just an attribute and normal C++, tell the compiler after that, once you've found all of these things, replace them with code that looks like this generic HIP kernel launch. And so this is exactly what I am implementing as a tool for Clang's front end. So the core of this work is a prototype of a source-to-source transformation tool built on Clang's front end, including a user interface that, exactly like the one I just showed, that is both user-friendly and allows for custom transformations. And as a proof of usefulness, I'm also in the process of writing an example implementation of Hippify using this tool. But once again, the use cases are in no way limited to just CUDA or HIP. So the user interface is pure C++ to minimize the learning curve for application developers, and is based on new C++ attributes that developers can use to define two sets of functions: matchers, which tell the front end what code to look for rewriting, and modifiers, which describe how to rewrite any matches that are found. And all of this is implemented with Clang's AST matcher to find the matching bits of code, and the rewriter interface to perform the source-to-source transformations. And so beyond just the Hippify example I showed, there are many, many potential use cases for this kind of automated customizable rewriting, including API updates, like when the library you're using changes a few function signatures, switching APIs or programming models like Hippify, selectively adding instrumentation calls to a performance measurement program like Tau, keeping device-specific code out of your main code base, like separate OpenMP and OpenMP target directives, adding error-checking asserts or checkpointing code, or adopting an application-specific performance portability layer, and see this excellent paper from the P3 HPC workshop at SC19 for more on that. So thank you for listening.